JMB, how are you all? I hope you all are good. I welcome you all to my YouTube channel. My name is Prince Ranpara. I'm a PhD scholar in the Department of Chemical Engineering at the Indian Institute of Technology, Ropur. So in today's lecture, we are going to understand one important concept of the chemical reaction engineering, which is the performance equation, right? So let's get started. So in today's lecture, we are going to derive the performance equations of continuously starting reactors CSTR, the plug flow reactors PFR, and the batch reactors, right? The first question which arises into our mind is what the term performance equation means. The second question which arises into our mind is what are the significance importance of the performance equations, right? The performance equation is the equation which connects reaction kinetics with the reactor design. Okay. In chemistry, we understand and we have studied how fast the reaction occurs, right? But as a chemical engineer, we need to understand and estimate how large volume of reactor is required in order to achieve the desired conversion, desired reactions, and reaction completes in efficiently manner, right? So the understanding of the performance equation will help us to understand the reaction kinetics in order to design the reactor designs, right? In order to design a reactor. Okay. Let's say now imagine that you are designing a reactor for the industries. You know the reaction kinetics, but you don't know how large volume of reactor is required in order to achieve the reaction in a efficiently manner, right? So this is exactly where the performance equation is the most powerful tool for the chemical engineers, right? So let's get started. We will derive the performance equation by using the concept of the design equations, right? Which means in order to derive the performance equation, we are going to utilize the concept of the design equations of the reactors, right? So let's get started. Okay. So first of all, we are deriving the performance equations of the CSTR by using the design equation of the CSTR. Okay. So let's say before beginning, there is one more question which arises into our mind is the design equations of the reactors are similar to the performance equation of the reactors, right? This question will arise in your mind. Okay, so let me make you very simplified, okay, and clear. Okay, so which will help you to understand in a better manner. Okay, so let's say by understanding and deriving the design equations of the continuously starting reactor, we'll understand how we how we how we carried out the mole balance across the reactors, right? Design by understanding the design equations of the CSTR, we'll understand how we carry out the mole balance across the reactor. Okay, but by understanding the performance equation, we'll understand the behavior of the reactor, right? The performance of the reactor, how the reactor will perform. Okay, it's called the performance equation, right? So by understanding the performance equation, we can understand the behavior of the reactor, right? In a practical manner, how the reactor will behave, right? Okay. So but the performance equation will be derived by using the concept of the design equations. Okay, so for those reasons, in order to derive the performance equation of CSTR, we are going to utilize the concept of the design equation of CSTR, right? So if you want to recall the how we derive the design equation of CSTR, I request you to please watch the previous lecture number 7, right? So let's say first of all we'll write the design equation of CSTR, which is formulated as V is equal to Fa naught minus Fa upon minus Ra, where Fa naught represent the initial molar flow rate. Oh, okay. Fa represent the final molar flow rates and minus Ra represent the rate of disappearance of reactants. Okay, and is also called as the mole balance equation, right? So let's say now by using the concept of the conversion, we are going to derive the equation 2, right? We are going to derive the equation 2. Now let's say the concept of the conversion I will make you understand in the next chapter number 2, but here I will make you understand in a very brief, right? The concept of the conversion, right? The conversion, which means how much reactants have been converted into the new products, right? It's called the conversion, right? For example, conversion will tell us about how much reactants has been reacted and converted into the new products, right? And how many reactants is left in the reaction environment. It's called the conversion, right? Which means how many number of molecules which we are feeding into the reactor, and how many out of those total molecules of the reactants, how many molecules have converted into the new product, and what are the remaining amount of reactants present in the reaction environment. It's called the conversion, right? Conversion of the reactants into the new product. It's called the conversion, right? So conversion can be formulated as with the three ways we can formulate the conversion, right? The conversion can be formulated in terms of molar flow rates, Fa naught or Fa. The conversion can be formulated as in terms of initial and final concentration of reactants, right? The conversion can also be formulated as in terms of moles, initial moles and the final moles, right? So let's say first of all, XA can be XA represent the conversion of reactants, right? So here we are going to derive, we are going to do the derivation with respect to the reactant A, right? With respect to reactant A. So for those reasons, we are writing the conversion of reactants A into the new product, right? So XA represents the conversion of A, which is formulated as initial molar flow rates minus Fa naught minus final molar flow rates Fa divided by initial molar flow rates Fa naught. In terms of concentration, the conversion can be defined as the initial concentration of reactants Ca naught minus final concentration of reactants Ca divided by initial concentration of Ca naught. Okay. In terms of mole, the conversion can be defined as the initial moles of reactants present in the reaction environment Na0 minus the final number of moles of reactants present in the reaction environment Na divided by initial moles Na0. Okay, so let's say here we are using the concept of conversion, okay, in terms of molar flow rates, right? So from here, XA is equal to Fa naught minus Fa upon Fa naught. We are deriving the equation 2 by doing the rearrangements, right? By performing the rearrangements, we will come up with the equation 2, right? Where in the equation 1 we are replacing Fa by its value, right? So Fa can be written as Fa naught minus Fa naught into XA. So we are taking common, we are commoning out Fa naught, right? So Fa naught into 1 minus XA. I hope you have understood the equation 2. Okay, so finally we obtained Fa is equal to Fa naught into 1 minus XA, right? So we are substituting the value of Fa in the equation 1. So volume will remain as it is. V is equal to Fa naught will remain as it is. Fa naught minus, we are substituting the value of Fa with this value, right? So this value, okay. Okay, so Fa is equal to Fa naught into 1 minus XA. We are substituting the value of Fa, right? So n divided by minus Ra will remain as it is. Okay, so finally we have obtained V is equal to Fa naught minus Fa naught into 1 minus XA upon minus Ra. Okay, now from this equation we are commoning out the Fa naught, right? So V is equal to Fa naught into 1 minus plus minus 1 minus plus XA, right? So finally from the numerator we are commoning out the Fa naught. Okay, so V is equal to Fa naught into 1 minus 1 plus XA upon minus Ra, right? From here the 1 will be cancelled off, right? So we are left with V is equal to Fa naught into XA upon minus Ra, right? So V is equal to Fa naught into XA upon minus Ra. I hope you have understood. Now we are rearranging the equation, okay? So we will get as V upon Fa naught is equal to XA upon minus Ra, right? I hope you have understood up to here the equation 3, right? Now let's say from here, so in equation 3, where you can see where we can correlate the volume, conversion rate of the reactions, the molar flow rates, right, with respect to each other, right? We can correlate all the terms with respect to each other, right? But what if we want to introduce some more terms, right? So let's say in equation 3, where we have the volume, right, where we have the volume, where we have the molar flow rates Fa naught, right, where we have the XA conversion, right, where we have the rate of disappearance of reactants, right? Okay, now let's say what if we want to incorporate the other term into the equation 3, then how we will proceed, right? So let's say if we want to incorporate the volumetric flow rates nu naught, the rate constant k, the space time tau, okay, the initial concentration ca naught, then how we can do, right? So let's say I will make you understand that how to incorporate all these important variables into the equation 3, right? So let's say first of all, let's say we know the volumetric flow rates, right? The volumetric flow rate is the ratio of molar flow rates to the concentration, right? So nu represent the final molar flow rates is the ratio of final concentration Fa to the final concentration Ca. Initial volumetric flow rate is denoted by nu naught is equal to initial molar flow rates Fa naught divided by the initial concentration Ca naught, right? Let's say from here we are making the subject as Fa, so Fa is equivalent to Ca into nu, right? Fa is equal to Ca into nu. From here we are making the subject as Fa naught, so where Fa naught is equivalent to Ca naught into nu naught, right? So in equation 3 we are replacing Fa naught by its value, right? We are replacing Fa naught by its value, okay? So let's say equation 3, we are modifying the equation 3 in order to incorporate all these important variables into the equation number 3, right? So let's say if we are carrying out the reaction at the constant volumetric flow rate, right, where the final volumetric flow rate is equivalent to the initial volumetric flow rate, right? Nu is equivalent to nu naught, okay? Now let's say we are incorporating the value of Fa naught into the equation number 3. So we will remain as it is, v divided by Fa naught. We are substituting Fa naught with its value Ca naught into nu naught. So v divided by Ca naught into nu naught is equivalent to, the right hand side will remain as it is, Xa upon minus Ra, Xa upon minus Ra, right? So here in equation 4 you can see we have introduced 4 new terms, right? In equation 4, from equation 3 to equation 4, okay? In equation 4 we have introduced 4 new terms, right? The first new term is Ca naught, initial concentration we have introduced, right? The second term is we have introduced volumetric flow rates nu naught, okay? The third term which we have introduced in equation 4 is the space time, right? Which is space time, okay? The space time is the ratio of volume by its volumetric flow rate. It's called the space time, right? So here you can see the ratio of volume to volumetric flow rate, it's denoted by the space time, okay? So the third term which we have introduced in the equation 4 is the space time, right? And the fourth term which we have introduced into the equation is the space velocity. Space velocity is the reciprocal of the space time, right? I hope you understood, okay? So by doing this small rearrangement from equation 3 to equation 4, where we have introduced more 4 terms into the equation 4, I hope you have understood, right? Now the space time, which means the space time is denoted by tau, is the ratio of volume to volumetric flow rate, right? Volumetric flow rate, we nu naught, we already know nu naught is equivalent to initial molar flow rate Fa naught divided by initial concentration Ca naught, right? So we are substituting the value of nu naught as Fa naught divided by Ca naught, right? So finally we'll get as tau is equal to V into Ca naught divided by Fa naught, right? It's called the space time. The units of space time are second, minute, hours, okay? I hope up to here you have understood. Let me make very simplified. Space time, which means the time required to process one reactor volume of the feed, is called the space time, okay? Time required to process one reactor volume of the feed is called the space time. Now, if we do the reciprocal of the space time, it's called the space velocity. So space velocity is denoted by small s, right? Space velocity is denoted by small s is equal to 1 upon tau. It's called the space velocity. The units of the space velocity are second inverse and minute inverse or hour inverse, right? Space velocity, which means the the space velocity, which means the amount of the reactor volume which we are feeding into the reactor, it's called the space velocity, right? Okay, I hope you understood. Okay, now let's say from in equation 4 we'll in the place of volume by volumetric flow rate, we can use the tau, right? Volume by volumetric flow rate is denoted by tau, right? So we'll modify the equation 4 as tau by Ca naught, right? So we can write tau by Ca naught is equivalent to the Xa upon minus Ra. The right hand side will remain as it is, Xa upon minus Ra. I hope you have understood, right? Okay, now let's say by analyzing the derivation, where you can see in the equation 3 and equation 6, you have same right hand side, right? In the right hand side, in equation 3, you have Xa upon minus Ra, and in equation 6, you can see you have Xa upon minus Ra, right? So due to those reasons, we can equalize equation 3 with equation 6, okay? So in equation 3, so by after equalizing the equation 3 with equation 6, what we'll get? We'll get V upon Fn naught is equal to Xa upon minus Ra is equal to tau upon Ca naught, right? So finally, we obtain the V upon Fn naught is equivalent to Xa upon minus Ra, okay? And Xa upon minus Ra is equivalent to tau upon Ca naught, equation 7, right? So finally here we have derived the performance equation of the continuously starting reactor, right? Okay, I hope you have understood. Okay, so by understanding the performance equations, right, by deriving and understanding the performance equation of continuously starting reactor, where we can understand and where we can correlates, where we can connect the reaction kinetics with the reactor design, right? So let's say by understanding the performance equation, where we can understand how large volume of reactor is required in order to carry out the reaction, right? How the reactor, how the reactions, how the rate of the reaction will change, how the concentration will change, what, how large volume of reactor is required, right? What will be the conversion by using the CSTR, okay? By using what size of, by using what size or what volume of CSTR, what conversion will obtain, right? So let's say for example, if we are having if we are having the higher rates of the reaction, right? So due to the higher rates of the reactants, the volume of the reactor will require very small, and the concentration of reactant will decrease with the very high very fast, right? So if you are having higher rates of the reaction, the concentration will decrease very fast, due to which will require the smaller volume of the reactor, right? For example, if you are having lower rates of the reaction, due to which the concentration of the reactants will decrease very slow, due to which will require a very large volume of the reactors, right? Okay, in order to achieve the desired conversion, how large volume of reactor is required, right? In order to achieve the in order to achieve the desired conversion, how, what molar flow rates I will set, okay? How large volume of reactor is required, what will be my rates of the reactions, okay? All these how the concentration will vary, all these things will be answered, right, by understanding the performance equation of the CSTR, right? I hope you have understood. Okay, so in the equation 7, where we represent the volume, the units are meter cube, liter, cubic, decimeter. If we not represent the initial molar flow rates, the units are moles per second, kilomoles per hour. The XA represent the conversion and is dimensionless, right? The minus Ra represent the reaction rate or rate of disappearing of reactants, right, from the reaction environment, right? The units are moles per meter cube second or kilomoles per meter cube per hour, okay? The tau represent the space time. The units are seconds, minute, hours. The Ca naught represent the initial concentration. The units are moles per meter cube or kilomoles per meter cube, okay? The small s represent the space velocity. The units are meter inverse, second inverse, and r inverse, right? I hope you have understood, right, how we derived and understand the performance equation of the CSTR, right? And why the performance equation is very important for the chemical engineers, right? For chemical engineers, why the performance equation plays a very vital role, right? I hope you have understood. Okay, so I request you to please make all the notes. Okay, I request you to please make all the notes. Okay, and in every lectures where I'm marking tick mark and stars. Those equations are very important. So I request you to please make the list of all the important equations with respect to the topics, right? So today's topic was we have derived how we derive the performance equation of the CSTR, right? So please write the topic performance equation of the CSTR, and you can make all the notes, okay? And you can also make additional notes or the list of all the important formulas, right? So I request you to please make all the notes, okay? So I hope you have made the notes right. Now let's say with the similar way, we'll derive the performance equation of the plug flow reactor, batch reactors, and the packed bed reactors, right? So let's get started. So here we are deriving the performance equation for the plug flow reactor, right? So let's say this diagram represents the plug flow reactor, right? So I have make you understand the important fundamental concept of the plug flow reactor in the lecture number 8, right? So if you want to recall, I request you to please watch the lecture number 8 where we have derived the design equation of the plug flow reactor, right? So let's say by using the similar concept, fundamental concept of the plug flow reactor and the design equation and the mole balance equation of the plug flow reactor, we'll try to derive the performance equation of the plug flow reactor, okay? So first of all, we'll write the mole balance equation of the plug flow reactor, right? Where RA is equal to dFA by dV, right? Now here, by using the concept of the conversion, where we are substituting FA with FA is equal to FA naught into 1 minus XA, right? So this equation 2 came from the mole balance equation, right? I hope you understood, right? XA is equal to FA naught minus FA upon FA naught, right? Upon FA naught. Okay, so from here, by rearranging, okay, we will get the equation 2. Okay, I hope you have understood. So same way we are plugging in the equation 2 into equation 1 in the place of FA, right? So RA is equal to d FA naught into 1 minus XA by dV, right? So we are substituting the value of the FA with its value, right? So RA is equal to d FA naught into 1 minus XA by dV. Okay, now we are further simplifying it, right? So FA naught represent the initial molar flow rates of reactants, right, which are entering into the plug flow reactor via inlet stream. Okay, so let's say FA naught is constant, okay, because initial molar flow rates are constant, right? Due to those reasons, we can take out FA naught of the differentiation, right? So FA naught we are taking out of the differentiation, right? So for those reasons, we can simplify in this form, right? So FA naught into differentiation of 1 divided by dV minus this minus FA naught into dXA by dV. I hope you have understood, right? Now the differentiation of constant will be equalized to 0, right? Due to those reasons, this equation will tends to 0, okay, because here we have constant FA naught and differentiation of 1, it's constant, right? So differentiation of 1 by dV will be equalized to 0. Due to those reasons, this entire term will equalize to 0. So we are remaining with this term, right? Minus FA naught dx by dV. So for those reasons, we can further write as RA is equal to minus FA naught dx by dV. I hope you have understood. So let's say from here we are making the subject as dV, right? And we are rearranging the equation. So finally we'll get dV is equal to minus FA naught dxa upon RA. Okay, I hope up to here you have understood. Equation 3 we have obtained. Now by applying, now this equation 3 represent the different very small differential element dV, right? This delta V, okay, very small differential element, right? So in order to account for the entire volume of the plug flow reactor, we'll try to apply the integration sign, right? So we are applying integration on the both the sides, right? So due to those reasons, we are applying integration on the both the sides of the equation 3. So integration dv from limits 0 to v, okay, from initial limit from v is equal to 0 to entire volume v. Okay, I hope you have understood. Here we have v is equal to 0 and here we have entire volume V. Okay, so integration from 0 to V dV is equal to Fa naught. We are taking out Fa of the integration because Fa naught is constant, right? Because the initial molar flow rate is constant. Due to those reasons, we are taking Fa naught out of the integration sign. So we are taking out Fa naught. So we are further writing as integration of 0 to xa dx upon minus ra, right? So I hope you have understood. Now further, if we integrate, integration of dv will remain as v from limit 0 to v. So v minus 0 is equal to v. So on the left hand side, we will only remain with the term v is equivalent to fa naught integration of 0 to xa dx upon minus ra. Okay, so finally here we have derived the performance equation of the plug flow reactor, right? So equation 4 represent the performance equation of the plug flow reactor. Okay, so let's say here, for example, if we carry out the reactions for the zeroth order reaction, first order reaction, second order reaction, third order reaction, or any other reactions, right? So we'll replace the R minus RA with the rate law, right? Let's say if you are having zeroth order reaction, so minus RA is equal to K. If you are having first order reaction, then minus RA is equal to KCA. If you are having second order reaction, minus RA is equal to KCA square. Okay, and likewise for any nth order reaction, we can replace with its rate law. Okay, and further we can simplify and derive the equation, performance equation of the plug flow reactor. And by using that performance equation, we can finally we can solve the numerical example. Okay, I hope you have understood. So here the performance equation of the plug flow reactor, which correlates the reaction kinetics with the design of the reactor, right? Where we can correlate volume, molar flow rates, conversion rate of the reactions, concentration, volumetric flow rate, space time, space velocity, okay, with respect to each others, right? I hope you have understood. So here we have completed the deriving of the performance equation of the plug flow reactor. Okay, I hope you have understood. So I request you to please make all the notes, right? Now we are deriving the performance equation of the batch reactor by using the concept of the design equation, right? So let's get started. So here we are deriving the performance equation for the batch reactor, right? So I have make you understand the fundamental concept of the batch reactor, right? If you want to recall, I request you to please watch lecture number 6, where we have understood how we derive the design equation of the plug flow reactor, right? So let's say here we are utilizing the concept of the design equation and the mole balance of the batch reactor in order to derive the performance equation of the batch reactor, right? So here, first of all, we are writing the mole balance, right? So in the case of batch reactor, where the inlet and outlet term is equivalent to 0, we remain with the generation term and the accumulation term, right? So first of all, we are writing the mole balance. So Ra into V is equal to dNA by dt. Okay. Now further, we are making from the equation 1, we are making the subject as Ra. So Ra is equal to dNA by dt into V. Okay, we are making the subject as Ra. So here V will go to the denominator on the right hand side. So Ra is equal to dNA by dt into V. Okay, further we can simplify here as differentiation of Na by V dt, right? So here Na by V will become Ca, because Ca we can write Ca is the concentration, right? So concentration, Ca concentration, we can write concentration as the ratio of moles of the reactants with respect to its volume. Okay, so concentration is the ratio of number of moles with respect to the volume. Okay, so Na by V represent the Ca. Okay, so d of Na by V upon dt we can convert as d of Ca by dt, right? By further using the concept of the conversion, we can derive similar way. Let's say by using the concept of the conversion, we have written the second equation, right? Fa is equal to Fa naught into 1 minus Xa. Okay, so here we have used the conversion as a function of the molar flow rates, right? So similar way here we can write Ca is equal to Ca naught into 1 minus Xa, right? Conversion in terms of concentration, right? Xa, I hope you have understood. Here we can write Xa let's say XA in terms of CA naught minus CA upon CA naught, right? Similar way, okay? So by using this concept, we can rearrange this equation, and finally we can get CA is equal to CA naught into 1 minus XA. So here we are putting the value of CA, okay? We are substituting the value of CA. So the differentiation of CA naught into 1 minus XA by dt, okay? So here we have obtained the equation 2. Further, we are simplifying the equation 2 as RA is equal to CA naught. So here similar way we are taking out CA naught of the differentiation, because the initial concentration of the reactants which we are feeding into the batch reactors will be constant. Due to those reasons we can take out CA naught out of the differentiation, right? So for those reasons we are taking CA naught out of the differentiation. So we will obtain the formula as RA is equal to CA naught differentiation of 1 by dt minus dxa by dt, right? CA naught into dxa by dt minus CA naught dxa by dt. Now similar way here the differentiation of constant will be equalized to 0, right? Due to those reasons this entire term will be equalized to 0, because differentiation of 1 is d by dt of 1 is 0, right? So due to those reasons this entire term will equalize to 0. So finally we are remaining with only this term on the right hand side, right? Minus a naught dx by dt. So finally we can write as Ra is equal to minus a naught dx by dt, right? Ra is equal to minus a naught dx by dt. I hope you have understood. Now furthermore we are making the subject as dt, okay? So we are making the subject as dt is equal to CA naught dxa by minus RA, right? By RA. So we can send this negative sign into the denominator, right? So finally we obtain the equation 4, which represent the differentiation dt is equal to CA naught dxa by minus RA, right? Now in order to account for the entire time, right, the time required to achieve the desired conversion, right? How much amount of time will be required in order to achieve the desired conversion, okay? So for those reasons we are applying integration on the both the side of the equation 4. So we are integrating from 0 to t, dt is equal to CA naught integration of 0 to xa dxa upon minus RA, right? Here we are taking CA naught out of the integration. Why? Because CA naught is constant, right? CA naught is constant, which means initial concentration of reactants which we are feeding into the batch reactor is constant, right? Due to those reasons we are taking CA naught out of the integration, right? So finally further after solving the integration of dt will be t from limit 0 to t. So t minus 0 is t, right? So on the left hand side we will remain with only t. So t is equal to CA naught integration of 0 to xa dxa upon minus RA. So here we have derived the performance equation of the batch reactor. I hope you have understood, right? So let's say if we have any order reaction, right? 0th order, first order, second, third, fourth, or any other reaction, right? So if with respect to the order of reaction, we'll use that rate law and we'll put the value of rate law over here, right? And further we'll solve accordingly, okay? Okay, I hope you understood. So here we can understand, we can correlate the reaction kinetics of the batch reactor with the designing of the batch reactors, right? And we can identify, analyze, and estimate how much amount of time will be required in order to achieve the desired conversion, okay? With respect to the rate of the reaction, with respect to the concentration, with respect to the molar flow rates, okay, and the space time, right? So similar way, I hope you understood how we derive the performance equation of the batch reactor, right? So here we have completed the deriving of the performance equation of the batch reactor. So I request you to please make all the notes, right? Now we are deriving performance equation for the packed bed reactor, right? So the derivation of the performance equation of the packed bed reactor will be similar, equivalent to the plug flow reactor. Why? Because in the both the case we are using the tubular reactors, right? Here the diagram represent the packed bed reactor or the fixed bed reactor, right? So here we are using the tubular reactor, same, okay? In the case of plug flow reactor we are using the tubular reactor, right? Only the main difference is here the tubular reactor is the whole space of the tubular reactor is empty, right? The hollow space of the tubular reactor is empty. And in the case of packed bed reactor, or the another name is fixed bed reactor, right? So in the case of packed bed reactor, where the hollow space of the tubular reactor is filled with the solid catalyst, right? Solid pellets, the support materials, inner support materials, right? Okay, so due to those reasons, we need to account the weight of the catalyst, right? How much amount of weight of the catalyst is required in order to achieve the desired conversion, desired conversion of the reactants, right? How the rate of the reaction will vary with respect to the weight of the catalyst, how the conversion will vary with respect to the weight of the catalyst, how the pressure will vary with respect to the weight of the catalyst, right? So similar way, we need to account for the weight of the catalyst, right? So similar way, we will derive the performance equation of the packed bed reactor, right? So similar, we are writing the mole balance of the packed bed reactor. So Ra is equal to dFA by dW. Okay, if you want to recall the fundamental understanding of the packed bed reactor, I request you to please watch lecture number 9, right, where we have derived the design equation of the packed bed reactor. Okay, now let's solve this. Okay, so first of all, we need to write the mole balance of the packed bed reactor. Ra is equal to dFA by dW, right? So similar way, by using the concept of the conversion, where we can use Fa is equal to Fa naught into 1 minus Xa, right? So we'll put the Fa value here. So Ra is equal to dFA by dFA naught into 1 minus Xa by dW, right? Now, similarly, the Fa naught, the initial molar flow rates, right? The initial molar flow rates are constant. Okay, the initial molar flow rates. Okay, due to those reasons, we are taking out the initial molar flow rates of the differentiation, right? So we can further simplify it as Fa naught into differentiation of 1 by dW. Okay, minus Fa naught into dxa by dW minus Fa naught dxa by dW, right? Now again, the differentiation of constant will be equalized to 0. So these term will become 0. I hope you understood, right? So Fa naught differentiation of 1 by dW will be equalized to 0, right? So we will remain with this term minus Fa naught dxa by dW. So finally, we can write as Ra is equal to minus Fa naught dxa upon dW, right? Now further, here we are making the subject as dW, right? So let's say dW is equivalent to minus Fa naught dxa upon Ra, right? I hope you have understood, okay? Now let's say here the dW, which means similar way, in the case of plug flow reactor, where we have account for the any infinitely small differential element of the volume, right? Similar way here, let's say we have account for the a very small delta W weight of the catalyst, right, in the packed bed reactor, right? But we need to account for the entire weight of the catalyst, right? So in order to account for the entire weight of the catalyst, we'll apply the integral sign on the both the sides of the equation, right? So we are applying integration on the both the sides of the equation 2. So integration of 0 to W dW. Okay, why? Because in the limits from 0 to W, because here at the starting point the weight of the catalyst is 0, right? At the starting point the weight of the catalyst is equivalent to 0, right? Weight of the catalyst is equal to 0, and here the weight of the catalyst will be equal to total weight of the catalyst, right? So due to those reasons, we are putting the limit as 0 to W. 0 to W, integration of 0 to W dW is equal to Fa naught integration of 0 to Xa dxa upon minus Ra. I hope up to here you have understood. We are solving the integral of dW will be W from limit 0 to W. So W minus 0 is equivalent to W, right? So on the left hand side, we will remain with the W is equivalent to Fa naught integration of 0 to Xa dxa upon minus Ra. I hope you have understood, right? So here we have derived the design. Here we have derived the performance equation of the packed bed reactor, right? Equation 4 represent the performance equation of the packed bed reactor, right? So by understanding the performance equation of the packed bed reactor, where we can correlate, where we can connect the reaction kinetics with the reactor design, right? So where we can understand how much amount of weight of the catalyst is required in order to achieve the desired conversion of the reactants, right? So how So let's say how the rate of the reaction will vary with respect to the weight of the catalyst, how the conversion will vary with respect to the weight of the catalyst, how the pressure will vary with respect to the weight of the catalyst, how the volumetric flow rates will vary with respect to the weight of the catalyst, right? How the molar flow rates will vary with the weight of the catalyst, right? So by understanding the performance equation of the packed bed reactor, we can correlate all these things, right? I hope you understood, right? So here we have completed the deriving of the performance equation for the peg bed reactor. Okay, I hope you have understood, right? So in order to conclude the today's lecture, in today's lecture we have derived and understand how we derive the performance equation for the continuously starting reactor, CSTR, plug flow reactor, PFR, batch reactors, and the peg bed reactors, PBR, right? I hope you understood. So I request you to please make all the notes. Okay, so now in the upcoming lectures we are going to solve numerical example where we'll try to compare all the reactors, right? The CSTR, plug flow reactor, batch reactors, right? So and we'll solve the one numerical example where we'll understand how all the reaction kinetics in the reactor design will vary with respect to the each and individual industrial reactors, right? And we'll solve numerical examples. Okay, so I hope you have understood, right? So until then, stay focused, keep learning, and stay curious. Thank you for watching my YouTube video. JMB.